Hey everyone! In this video our objectives are the following. We are going to discern between bond polarity and molecular polarity. In doing so, we are going to also use polarity to distinguish between non-polar covalent, polar covalent, and ionic bonds. So to begin, we must discuss this term polarity. Polarity is an uneven charge distribution. Now this is not unlike perhaps a magnet that you've seen where you have a positive side and a negative side, or a battery where you have to put the batteries in a device correctly where there is a positive side and a negative side, or even the planet itself where we have a north pole and a south pole, and we have an uneven distribution of charges. Now let's look at the term bond polarity. Now we do know that atoms, to bond with one another, need to either transfer electrons from one atom to another, in the example of an ionic bond, where a metal loses an electron to a nonmetal, or in the case of covalent bonding, where we have nonmetals sharing electrons. So here are a whole bunch of examples of some covalently bonded atoms. One fluorine bonded to another, they are sharing electrons, so there are two electrons in between them. Here's oxygen that is sharing two pairs of electrons, forming a double bond. Nitrogen bonded to nitrogen, sharing 6 electrons in a triple bond. Here is carbon dioxide, where this carbon and that oxygen are sharing two pairs of electrons, so that's 4 electrons total, while this carbon, the same carbon, is sharing the same amount of electrons with an oxygen on the opposite side. Here is a hydrogen bonded to an oxygen, and that oxygen is also bonded to another hydrogen, sharing 2 electrons each. Here's a central carbon bonded to 4 separate hydrogens at the same time, forming 4 separate single bonds. Here's a carbon double bonded to a sulfur, while it is also single bonded to one hydrogen and single bonded to another. So when we use the term bond polarity, we are talking about the distribution of charges between the two atoms of a bond. So let me grab a red pen and highlight. So we have one bond here, we would be interested in its polarity. One double bond here, interested in its polarity. A triple bond here, it's going to have a polarity. There's going to be a polarity between this carbon and this oxygen, and a different, well, maybe different polarity between that carbon and that oxygen. Looking at the H2O, there's going to be a bond polarity between the hydrogen and the one hydrogen and the oxygen, and the other hydrogen and the oxygen. Same for this molecule right here. The carbon is going to have a bond polarity between that hydrogen, bond polarity between that hydrogen, bond polarity between that one and this one. And last, this one's most interesting. There is going to be a bond polarity between that carbon and hydrogen, that carbon and hydrogen, but there's going to be a different relationship between the bond polarities between the sulfur and this carbon. So let's look at this even more deeply. Now the only way to look at this more deeply successfully is to reintroduce the term electronegativity. Remember, electronegativity has everything to do with how strong an atom pulls on neighboring electrons, sometimes to steal them, and in the case of covalent bondings, to share them. So electronegativity will govern whether or not an atom is pulling on the electrons strong enough to steal them or just merely share them. And if they are sharing them, are they sharing them evenly? So let's look at these values. If we take the electronegativity values of two separate atoms, okay, and put them next to each other, if that value, the difference between those values, falls between 0.0 and 0.4, the bond between those two atoms is considered a non-polar, no uneven distribution of charges, so non-polar covalent bond. If the value falls between 0.5 and 1.7, it is a polar covalent bond. So while the electrons are still being shared, they're not being shared evenly. Now, if that value is greater than 1.7, then that only occurs when we have a nonmetal bonding to a metal and a complete transfer of electrons from one to another, so they are not sharing them whatsoever. Let's take a look at a couple of examples here. Chlorine bonded to chlorine. Now, chlorine, as we can see from our periodic table, has an atomic number of 17. And I know we're going to be dealing with boron later, bromine, and so that's 35. So let's just remember those for a moment, okay, so that we could go ahead and find those electronegativity values, harness them, and use them. So chlorine's electronegativity is, it's atomic number 17, there's chlorine, it's 3.2. And we did say bromine, where are you? There it is. Bromine is 3.0. Let's remember that as we put them to use. Actually, I already forgot them. Chlorine was 3.2, bromine was 3.0. So, what can we do with this? 3.2 minus 3.2 is equal to 0. So, if the electronegativity difference is equal to 0, then it is a non-polar covalent bond. Again, meaning that the electrons shared between these two chlorines is evenly distributed. They're no more on this side than they are on that side. Now, as far as the bond between bromine and chlorine, that was 3.0 versus 3.2. Now we only care about the difference, so I don't care if it's a negative or positive value. 0.2, once again, falling in this range. It is a non-polar covalent bond. And now let's take a look at a few other examples. Oxygen to oxygen and oxygen to sulfur. Well, oxygen's atomic number is, moving the wrong thing, there's oxygen. Oxygen is atomic number 8 and sulfur is 16. Let's now get that out of the way. So oxygen's electronegativity is 3.4, while sulfur's is 2.6. I see it there on the bottom. So 3.4 and 2.6. 3.4, 2.6. I'm only putting it there so that we could see it easier later. So 3.4 minus 3.4, because it's oxygen bonded to oxygen, again that's 0. It is a non-polar covalent bond. Now let's take this example down here. Oxygen at 3.4 electronegativity bonded to sulfur with 2.6. The difference is equal to 0.8, and that falls in this range. And, well, let me grab another slide and show you what that looks like. Alright, so here again we have the oxygen double bonded to the sulfur. Keep in mind that even though this is a double bond, it's considered to be a single individual bond, just called a double bond, sharing 4 electrons. But more to the point, it has an electronegativity difference of 0.8, which makes this a polar covalent bond. And the way we could identify the polarity here is to first identify which atom is pulling on those electrons more. Now 3.4 is certainly higher than 2.6, so the oxygen is pulling on the electrons more. They're still being shared. So we can say that the oxygen has a slight negative charge because the electrons will be in orbit around the oxygen more frequently than the sulfur. So if the oxygen has a slight negative charge, the sulfur must have a slight positive charge. Now this leads us to the term molecular polarity. This is different than just bond polarity. It is the charge distribution for the entire molecule, which means that all of the individual bond polarities and the symmetry of the three-dimensional molecular shape must be considered. So now let's put this into practice. Here we have one oxygen double bounded to another oxygen, that making it a molecule. It's not a compound because they're both oxygen. Now both of their electronegativity values are 3.4, giving it a final electronegativity difference of 0, which makes it a nonpolar covalent bond. But let's take a look at this one. Now we have to be very careful. We have to make sure that we are examining the bond, not the entire thing. So we are examining oxygen chemically bound to carbon. They are sharing 4 electrons because this is a double bond. The 3.4 value belongs to oxygen. The 2.6 value belongs to carbon. And that gives us a difference of 0.8, making it a polar covalent bond. But which one is now more interested or pulling on those electrons more? And it, of course, is the oxygen. So oxygen acquires a slightly negative charge, while carbon is a slightly positive. Now what's true for these two, the carbon and the oxygen here, must also be true for this carbon and oxygen, but towards the other side. So this oxygen is going to be slightly negative. Now we've considered both bonds. Now we have to consider the entire molecule. And if in fact we split this molecule in half, we would see that it's almost like a tug of war. The degree to which this oxygen is pulling the electrons more in that direction is equal but opposite to that going the other way. So even though we do have 2 separate polar bonds here, we can say that the entire molecule together as a whole is non-polar. Conversely, let's look at what's below. Get this completely out of the way. And here we have NH3. Again, we want to examine the individual bonds. And we have hydrogen with a 2.2 and a nitrogen with a 3.0. Again, 0.8 electronegativity difference, making the bond polar. Now, if that's the case, this bond must be polar, and this one as well. Now, similar to what we just discussed above, let's take a look at the symmetry of the molecule. From side to side, the line should have gone through the end. From side to side, yes, they would be pulling evenly, but this time nitrogen would be pulling on the electrons more. So from side to side, left to right, yeah, there's really no difference. But what about top to bottom? Do we have equal but opposite there? The answer, of course, is no. So it does have polar bonds, and in this case, the entire molecule as a whole is also polar. So what might help you when dealing with molecular polarity, and again, that's for the entire molecule, not just little pieces, is to consider this mnemonic. It's SNAP. And what SNAP stands for is symmetrical, is nonpolar, while asymmetrical is polar. Of course, we mean by that is nonpolar covalent and polar covalent. So to summarize, what you need to do is you need to look deep inside a molecule to see if the electrons are being shared evenly or unevenly, and to see if a molecule is symmetrical or asymmetrical.